Statistical process control is a method of quality control which uses statistical methods. SPC is applied in order to monitor and control a process. Monitoring and controlling the process ensures that it operates at its full potential. At its full potential, the process can make as much conforming products as possible with a minimum of waste. SPC can be applied to any process where the conforming product output can be measured. Key tools used in SPC include control charts, a focus on continuous improvement, and the design of experiments. An example of a process where SPC is applied is manufacturing lines. Overview. Objective analysis of variation. SPC must be practiced in two phases. The first phase is the initial establishment of the process, and the second phase is the regular production use of the process. In the second phase, a decision of the period to be examined must be made, depending upon the change in 4M conditions and wear rate of parts used in the manufacturing process. Emphasis on early detection and advantage of SPC over other methods of quality control, such as inspection, is that it emphasizes early detection and prevention of problems, rather than the correction of problems after they have occurred. Increasing rate of production. In addition to reducing waste, SPC can lead to a reduction in the time required to produce the product. SPC makes it less likely the finished products will need to be reworked. Limitations. SPC is applied to reduce or eliminate process waste. This, in turn, eliminates the need for the process step of post-manufacture inspection. The success of SPC relies not only on the skill with which it is applied, but also on how suitable or amenable the process is to SPC. In some cases, it may be difficult to judge when the application of SPC is appropriate. History. SPC was pioneered by Walter A. Showhart at Bell Laboratories in the early 1920s. Showhart developed the control chart in 1924 and the concept of a state of statistical control. Statistical control is equivalent to the concept of exchangeability developed by logician William Ernest Johnson also in 1924 in his book Logic. Part 3. The Logical Foundations of Science. Along with a gifted team at AT&T that included Harold Dodge and Harry Romig, he worked to put sampling inspection on a rational statistical basis as well. Showhart consulted with Colonel Leslie E. Simon in the application of control charts to munitions manufacture at the Army's Picatinny Arsenal in 1934. That successful application helped convince Army Ordnance to engage AT&T's George Edwards to consult on the use of statistical quality control among its divisions and contractors at the outbreak of World War II. Edwards Deming invited Showhart to speak at the Graduate School of the U.S. Department of Agriculture, and served as the editor of Showhart's book Statistical Method from the Viewpoint of Quality Control, which was the result of that lecture. Deming was an important architect of the quality control short courses that trained American industry in the new techniques during World War II. The graduates of these wartime courses formed a new professional society in 1945, the American Society for Quality Control, which elected Edwards as its first president. Deming traveled to Japan during the Allied occupation, and met with the Union of Japanese Scientists and Engineers in an effort to introduce SPC methods to Japanese industry. Common and special sources of variation. Showhart read the new statistical theories coming out of Britain, especially the work of William Seeley Gossett, Carl Pearson, and Ronald Fisher. However, he understood that data from physical processes seldom produced a normal distribution curve, that is, a Gaussian distribution or bell curve. He discovered that data from measurements of variation in manufacturing did not always behave the way as data from measurements of natural phenomena. Schohart concluded that while every process displays variation, some processes display variation that is natural to the process. These processes were described as in control. Other processes additionally display variation that is not present in the causal system of the process at all times, and these were described as not in control. Application to non-manufacturing processes. In 1988, the Software Engineering Institute suggested that SPC could be applied to non-manufacturing processes, such as software engineering processes. In the Capability Maturity Model, the Level 4 and Level 5 practices of the Capability Maturity Model integration use this concept. The notion that SPC is a useful tool when applied to non-repetitive, knowledge-intensive processes such as research and development or systems engineering has encountered skepticism and remains controversial. In his seminal article No Silver Bullet, Fred Brooks points out that the complexity, conformance requirements, changeability, and invisibility of software results in inherent and essential variation that cannot be removed. This implies that SPC is less effective in the domain of software development than in, e.g., manufacturing. In 2014, a method for data validation of measurement data, based on SPC, was tried out. The method enabled the user to validate data containing static wave components, a requirement when working on hydropower plants where slowly damping surges are abundant during normal operation. Variation in manufacturing. In manufacturing, quality is defined as conformance to specification. However, no two products or characteristics are ever exactly the same, because any process contains many sources of variability. In mass manufacturing, traditionally, the quality of a finished article is ensured by post-manufacturing inspection of the product. Each article may be accepted or rejected according to how well it meets its design specifications. In contrast, SPC uses statistical tools to observe the performance of the production process in order to detect significant variations before they result in the production of a substandard article. Any source of variation at any point of time in a process will fall into one of two classes. 1. Common causes, sometimes referred to as non-assignable, normal sources of variation. It refers to many sources of variation that consistently acts on process. These types of causes produce a stable and repeatable distribution over time. 2. Special causes, sometimes referred to as assignable sources of variation. It refers to any factor causing variation that affects only some of the process output. They are often intermittent and unpredictable. Most processes have many sources of variation. Most of them are minor and may be ignored if the dominant sources of variation are identified. However, resources for change can be focused on them. If the dominant assignable sources of variation are detected, potentially they can be identified and removed. Once removed, the process is said to be stable. When a process is stable, its variation should remain within a known set of limits. That is, at least, until another assignable source of variation occurs. For example, a breakfast cereal packaging line may be designed to fill each cereal box with 500 grams of cereal. Some boxes will have slightly more than 500 grams, and some will have slightly less. When the package weights are measured, the data will demonstrate a distribution of net weights. If the production process, its inputs, or its environment change, the distribution of the data will change. For example, as the cams and pulleys of the machinery wear, the cereal filling machine may put more than the specified amount of cereal into each box. Although this might benefit the customer, from the manufacturer's point of view, this is wasteful and increases the cost of production. If the manufacturer finds the change in its source in a timely manner, the change can be corrected. Application of SPC. The application of SPC involves three main phases of activity. Understanding the process and the specification limits. Eliminating assignable sources of variation, so that the process is stable. Monitoring the ongoing production process, assisted by the use of control charts, to detect significant changes of mean or variation. Control charts. The data from measurements of variations at points on the process map is monitored using control charts. Control charts attempt to differentiate assignable sources of variation from common sources. Common sources, because they are an expected part of the process, are of much less concern to the manufacturer than assignable sources. Using control charts is a continuous activity, ongoing over time. Stable process. When the process does not trigger any of the control chart detection rules for the control chart, it is said to be stable. A process capability analysis may be performed on a stable process to predict the ability of the process to produce conforming product in the future. Excessive variation. When the process triggers any of the control chart detection rules, other activities may be performed to identify the source of the excessive variation. The tools used in these extra activities include Ishikawa diagrams, designed experiments, and Pareto charts. Designed experiments are a means of objectively quantifying the relative importance of sources of variation. Once the sources of variation have been quantified, actions may be taken to reduce or eliminate them. Methods of eliminating a source of variation might include development of standards, staff training, error-proofing, and changes to the process itself or its inputs. Mathematics of control charts. Digital control charts use logic-based rules that determine derived values which signal the need for correction. For example, derived value equals last value plus average absolute difference between the last n numbers. Bibliography. Barlow, E., and Irony, Z. Foundations of Statistical Quality Control, in Ghosh and Patik, P.K. Current Issues in Statistical Inference. Essays in Honor of D. Basu, Hayward, C.A., Institute of Mathematical Statistics, 99-112, Bergman. Conceptualistic Pragmatism. A Framework for Bayesian Analysis, i.e. Transactions, 41, 86-93. Deming, W.E. On Probability as a Basis for Action, The American Statistician, 29, 146-152. Out of the Crisis. Quality, Productivity and Competitive Position. ISBN 0-521-30553-5. Oakland, J. Statistical Process Control. ISBN 0-7506-57669. Salasinski, T.S.P.C., Statistical Process Control. The Warsaw University of Technology Publishing House. ISBN 978-83-7814-319-2. Shohart, W.A. Economic Control of Quality of Manufactured Product. ISBN 0-87389-076-0. Statistical Method from the Viewpoint of Quality Control. ISBN 0-486-65232-7. Wheeler, D.J. Normality and the Process Behavior Chart. ISBN 0-945320566-6. Wheeler, D.J. and Chambers, D.S. Understanding Statistical Process Control. ISBN 0-945320132. Wheeler, Donald J. Understanding Variation. The Key to Managing Chaos. 2nd edition. SPC Press, Inc. ISBN 0-945320531. Wise, Stephen A., and Fair, Douglas C. Innovative Control Charting. Practical SPC Solutions for Today's Manufacturing Environment. ASQ Quality Press. ISBN 0-87389-385-9. Zabel, L. Predicting the Unpredictable. Synthesis 90. 205. DOI 10.1007, BF 004855351.